Good morning. Thank you for coming so early to my last talk. I'm going to talk about kinetic data structures, which I know a number of people here are very interested in. And I'm going to talk about kinetic data structures for computational geometry and also for graph drawing. So everything I know about kinetic data structures I learned from my student, Zahid Rahmati, who came to Victoria and now is back working in a University of Tehran. He had written a master's thesis on kinetic data structures, and he wanted to continue that work in Canada. So he had to teach his supervisors about kinetic data structures. We got interested in it. And then along the way, since I'm interested in graph drawing, I said, well, what would kinetic data structures look like in a graph drawing context? So we're going to see really three things today. We've been talking about geometry problems for things that move. You'll remember at the beginning we talked about reconfiguration problems for chains of links. Can you move from one configuration to another? So some movement idea involved there. And then we also talked about navigation problems and localization problems for robots. So there we changed from a high degree of freedom situation, chains of n links, to a low degree one, just a point robot or a vacuum cleaner robot moving down the hallway. And we took a look in that context at a computational geometry point of view for localization. We had these overlay maps and visibility graphs and edge visibilities and so forth. And then we got a little more practical and we said, well, what would a robotics person do with a problem like this, and ideas like we had coming from computational geometry? Well, they start sampling points and figuring out how to sample points and using computational geometry ideas to figure out good places to sample. You do simulation, you do experiments, and see what seems to work better in practice. It gets much harder to validate or evaluate your algorithms and say this thing is better than something else. Whereas in computational geometry, we're used to talking about worst case analysis using a real RAM model of computation. And there we can be precise in that context, but what it means in practice is debatable. So it's a different world when you move to the world of simulation, and a different world still when you move to a world where you're actually trying to move a robot down the hallway and it's subject to all kinds of sources of error. The batteries of some beacons are weaker than the batteries of other beacons. The cone doesn't precisely model what the beacon can see. There's all kinds of approximations involved. I think some of you people talking about sources of error have seen some of that kind of analysis from the point of view of computational geometry, but real-world sources of error involves doing lots of real experiments, seeing what a beacon can actually see. It involves a lot of getting down on the floor and fiddling around with it and doing repeated trials and making approximations. So then we shifted a little bit and talked about geometry, how we can use geometry to express relationships like graph relationships. We have objects, geometric objects, and we use the relationships between them to express edge relationships in an abstract combinatorial graph. And we wonder what kinds of geometric relationships have what kind of expressive power in terms of expressing graphs. And we also took a look at a fixed parameter tractability approach for that kind of situation. Fixed parameter tractability for a hard graph drawing problems. So today we're going to synthesize some of those themes in a way: movement problems, geometry problems. We're going to talk about data structures for things that move. So we're going to have points that are moving, and we're going to talk about these kinetic data structures that keep track of the relationships between the points as they move. And what we're also going to see is how those ideas can possibly apply to a graph drawing situation. We're trying to find a nice layout of a graph, but now we're going to lay the graph out on vertices, points that are moving. How do we draw a graph nicely at fixed locations for the vertices when the fixed locations, in fact, aren't so fixed at all, they're moving? So how do we combine all this movement and geometry and graph drawing? But no FPT today, no fixed parameter tractability. So the talk is going to have 3 parts. One is an introduction to kinetic data structures. And I'm sure many of you are already familiar, more familiar than I am with kinetic data structures. You've been to the pre-course workshop here. Oh, thank you. And you've seen examples of kinetic data structures. So please bear with me while I briefly review what I understand kinetic data structures are about. And then I'm going to show you an example of a kinetic data structure approach to a couple of computational geometry problems. I'm not going to go into a lot of technical detail, but I think there are a couple of nice ideas there that serve to illustrate what the main ideas of kinetic data structures are. And then I'm also, in the third part, going to talk about kinetic data structures for a graph drawing problem. And the graph drawing problem is not going to be a very compelling, natural problem. It's just that we wanted to start a new area of exploration. What does it look like to draw graphs on points that move? So first part, introduction to kinetic data structures. So what's the idea of a kinetic data structure? You have a collection. It's not just a data structure. It's a collection of algorithms and data structures that are designed to work together to deal with points that are moving. It's a concept that was introduced by Leo Gibas and one of his students, Bosch, in the late 1990s, together with John Hirschberger. So they developed that concept, and Bosch wrote a PhD thesis on that topic. It's now a familiar concept, kinetic data structures, and there's a substantial body of work about kinetic data structures. But a lot of the key definitions and terms and concepts come from that initial work back in the late 1990s. And sometimes you look at these terms and you say, well, why that? Why is that the definition? And it's just accepted. It's been, some of the definitions, I understand, has been accepted since they were originally defined. But people don't seem to have been questioning those definitions or playing with changing them or just accepting the original structure and still exploring what you can do with that. There's been a little bit of work in implementation. There was a guy, Daniel Russell, who did a PhD thesis at Stanford with Leo Gibas, and then a postdoc or spent part of his PhD studies at INRIA working on implementations of kinetic data structures, trying to get implementations that are something one could publish and invite the world to use, which is a high level of implementation. Hasn't been a lot of implementation work. I'm not really aware of publicly available implementations of kinetic data structures other than Daniel Russell's work. So what's the motivation for looking at kinetic data structures? Well, remember, this is, if you think back to late 1990s, most of you were born by then. Okay, yeah, 1990s or early on. So what's happening is, back in those good old days, is wireless technology and GPS technology. So we have the technology, as of late 1990s, to track points that move. We get lots of data about those points. And we want to be able to answer questions about point sets that are moving. We want to be able to answer those questions quickly. So virtual reality, for example, computer games, it's generating data about points that are moving in virtual worlds, players that are moving in the real world. Now there's games that you play in the street and people are moving around and doing things. So lots of moving points, whether they're in virtual worlds or in the real world, and we want to ask what kinds of computational problems arise from having all that data and how do we deal with it. That was the motivation. And Leo Gibas wrote a book with Fang Zhao, who at that time was in Silicon Valley I believe he was working in one of the research labs in a big company there. And in any case, he's now moved back to China. But they wrote this introductory book about wireless sensor networks, an information processing approach. I like very much the picture on the cover of the book. These are probably Canadian geese, these huge geese birds that migrate and form these wonderful V-shaped patterns as they fly, so that the bird is like bicycle racers. The bird wants to slipstream, take advantage of the bird ahead of it to reduce the wind resistance as it flies, so it doesn't expend so much energy. So they're wonderful things to study. And I think the idea that this evokes this picture is that somehow these birds are communicating with one another, wirelessly, sure, maybe not electronically, but they're using visual cues, they're using acoustic cues, they're communicating with one another, and somehow they're arranging themselves as they fly. That's one thing that's going on there with those moving objects. Another perspective on this is that we can now, if we're not a Canadian goose, we can now imagine studying these things. We can put radio collars on them without destroying the bird. We can track them, find out where they are as they move, and study relationships of these objects as they move. So this picture is just meant to convey, well, here's a group of bicycle riders. Hard to see, I can't quite read this, what city they're in. I don't remember where I got the photograph. But you can imagine, oh, okay, so there's an international sign. It's definitely not the U.S. They're riding along. They have cell phones. One can follow where it is they're traveling. They want to be followed. We have a group in the geography department at UVic, where they have a project to study problems that bicycle riders encounter. So Victoria is trying to be sustainable, is trying to encourage bicycle riding, but what happens when you mix bicycles and traffic is that you have accidents. Even if the bicycles are moving along bicycle paths with no trucks, occasionally there's intersections with streets, the bicycles run into one another and so forth. And so the idea is to get bicycle riders to volunteer to be tracked. And whenever they have an accident or a collision or see something, experience something that's bad for bicycle riders, they send in a remark about that, they tag the location and the time and so forth. So all this data gets accumulated, and then they make a bicycle map for people who ride bicycles in Victoria and say, watch out for these hot spots, these are dangerous places. They lobby the city council that something should be done about these dangerous places, more signs, more speed bumps, this kind of thing. So there's all kinds of things one can imagine doing with moving points. Here's some military aircraft. They got to coordinate with one another, want to know what they're going. Here's more birds. Here's a scene that's meant to evoke a virtual world. So this is a picture from a video game. And here one can imagine knowing, as we assumed for kinetic data structures, that these points are moving, the cars are moving along a particular direction with a particular speed, say, and then maybe from time to time something that's moving straight is going to turn right or come to a stop. There's going to be, from time to time, changes in the intended paths of these vehicles, and how might you track that information even within the game of what's going to happen next and what pairs of trucks are going to be closest to one another and this kind of thing. So I just showed you those pictures to get you thinking about what kinds of situations we might want to ask questions about on sets of moving points. So here's the situation for a kinetic data structure framework. This is just a rough idea. It took me a while to understand from Zahed what kinetic data structures were about, because the people who are experts in the area are so used to using the terminology of the area that if you don't understand the meaning of the word from some context, it's just kind of there's a little barrier to understanding what they're doing. So the situation is this. We have a set of moving points or bodies, maybe they're geese or bicycle riders or points or representing objects in a video game, and they're moving according to some nice known or estimated trajectories, which in general is not a very good assumption, is it? Cars change the speed. They may be going down the highway, so you know the path of the car, but it's going to be slowing down and speeding up for all kinds of reasons, weaving in and out of traffic. You're certainly not going to have an accurate model of the trajectory of a car in terms of low-degree polynomial equations for the x and y coordinates of the car. You're not. but we have to start somewhere, so that's an assumption that's typically made in kinetic data structures, that you know the coordinates of the points, the x, y coordinates of points, as functions of time, x of t, y of t. So that's telling you not just the position of the point, but also where it is in time. And those are low-degree polynomials bounded by a constant. So why that assumption? Well, it makes it easy to do, it facilitates doing analysis, because you can say how many times these trajectories are going to cross one another, for example. So that's going to have implications about the size of your, the properties of your data structure. So that's why people make some assumption. It facilitates analysis. It's not a very practical assumption, not an engineering assumption. And then we also have some question we want to be able to answer at unknown future times about this set of points. We might want to know, simple example, points moving around, which pair of those geese, okay, x, y, z coordinates, and we certainly don't have precise estimates of their trajectories, but we can imagine we have a model. They're going south if it's winter time. So we want to ask some question like, which pair of geese are the closest geese? Which pair of cars are the closest of closest? Which pair of airplanes are closest together? We have to pay attention to that pair of airplanes because they might be in danger of crashing. If we were a radio control officer in a guiding aircraft to land, we want to make sure they stay spaced apart. So we want to focus attention on the closest pair and not pairs that are well spaced. So we have some question like that we would like to answer from time to time. And we can't say, at 3 o'clock, I'm going to ask this question. We just know from time to time, somebody's going to ask this question, or we're going to ask this question. And we want to be able to answer the question correctly. And, So we call the current answer to the question. So initially, we start off with an answer to the question, what's the closest pair of points? That's called an attribute of the point set in the language of people who study kinetic data structures. An attribute of the point set is just the answer to this question that we're interested in following. So point sets have all kinds of attributes, the convex hull of the point set, the Voronoi diagram of the point set. They have all kinds of attributes. So when we ask a question, we have a particular attribute, property of the point set that we want to be able to convey on the spot and correctly. So as the points move, the correct answer to this question is going to change. The pair of points that are closest together is going to change as the points move around. We want to be prepared to answer that. So one approach to doing this is just start from scratch. Every time you want to answer the question, see where the points are and solve the problem right then. But the whole idea of kinetic data structures is that maybe if you start off with the correct answer, as the points move, you do some updates in whatever information you're following about the points, so that when the question is asked, you can immediately respond without having to recompute what the answer is from scratch. So that means along the way, you have to do some updating, you have to do some house cleaning, so to speak, in order to be able to say, okay, this is the answer. Or you just maintain the correct answer all the time so that when somebody asks, you can just say, this is the answer. So you need methods to do updates, too. You might have an estimate of your trajectory that changes. A car turns right at that intersection. Now you have a new trajectory for that automobile. And now that's going to change your internal representations of trajectories. Now your knowledge of properties of points, maybe you're doing something like maintaining for triples for each pair is the third point on the right side or the left side of a directed line, something like that. That kind of structure you might be maintaining internally, it's going to change. So you want to be able to do updates quickly. If you're spending too much time doing updates, then you might as well just recompute the answer from the start each time someone asks the question. So you don't want to spend a lot of time doing updates. And of course, you don't want to have huge running times doing this or huge amounts of space. What would be the point? So here's a picture. Our input is some moving set of points. And then we process this input with our kinetic data structure. And then the output at any time is this attribute of the moving points, the property that we're interested in. So here's this assumption, not very realistic assumption, but this is the assumption that's made. You have some known trajectories, or know the paths of the points. We can compute when those paths are going to intersect ahead of time. So if the trajectories don't change, we know at each point, we know when those critical situations are going to be. We can make an event queue of times in which the relationships between points are going to change. Their trajectories cross, for example. And from time to time, it may be that a trajectory changes, and then we've got to recompute our idea about when trajectories intersect. But that's something we want the kinetic data structure to be able to do well. So here's a couple of key terms for kinetic data structures. One is the idea of a certificate. And it's just some statement about the relationship among a set of points. For example, I can say, here's 2 points A and B. Here's a point C. Is C to the right of the directed line through A and B? True or false? So it's a question about the set of points that has an answer, true or false. And we're going to maintain certain certificates as part of our kinetic data structure for answering a problem. We'll see a nice example of certificates when we look at the graph drawing problem. And an event is when a certificate fails. A certificate that had the Boolean answer true now suddenly turns to false. For example, maybe 3 points become collinear, and now something that used to be true is about to become false. So these are events. These are called events. So there are two kinds of events. There are internal events and external events. And that's described down here in efficiency. So external events are situations where the answer to the question you're asking changes. So what's the closest point to point A suddenly has a different answer. That's an external event. But an internal event is when one of these certificates that you're maintaining as part of your data structure changes from a true statement to a false statement. Maybe the closest pair doesn't change, but some information that you're maintaining changes. So part of your design of the kinetic data structure is to design these certificates. And we'll see examples of that. So if the ratio between the worst case number of internal events, these are this internal information you have to maintain, and the worst case number of external events should be something like order polylog of n, where n is the number of moving points. Then we say the kinetic data structure is efficient. What's efficient about that? Why polylog n? That's just what people found reasonable and appealing in the late late 90s. It's just, we just accept that. That's the rule. We're aiming for this ratio of worst case internal to worst case external events as being a logarithmic. And it's just a way of expressing the idea. If we're doing too much housekeeping, then it's not worth the effort. So what are some other performance criteria? Again, these start from the very beginning of work in kinetic data structures. And every paper has got to start off with a little reminder to everyone, what are the performance criteria? So responsiveness, that's how much time it takes you to handle an event, either an internal or external event. And what people aim for is polylog time. Compactness is how many of these certificates you need to maintain at any time. We'll see later what's a certificate. So compact means you're using n log to some constant n number of certificates. And locality means the number of certificates that's associated with any point that's moving. And it's local if no point is using more than polylog certificates. So those are the performance criteria. And the experts throw these words around: responsive, compact, local, and efficient, very fluently. And I always have to stop and think which one means which. Okay, so let's take a look at computational geometry, pure kinetic data structure approach to a couple of problems. This is work led by Zahed, and I think there's some very nice, elegant ideas here that we can understand today. So these are slides taken from a paper called K-nearest neighbors and reverse K-nearest neighbors of moving point sets. And Valerie King, she's my colleague at UVic. She was Zahed's other co-supervisor. Actually, he was supervising us, but anyway, we were supervising him. So we're going to state the problem, talk about potential applications, and give some results and insights. So K-nearest neighbor problem, that's a familiar and natural idea. You have a set of points in the plane, and for each point, you want to know what's the closest neighbor of that point, or more generally, you want to know the k closest neighbors to that point. And that's something you'd like to know for every point. So that's the all k nearest neighbors problem. Find for each point all the nearest neighbors. So if k is equal to 1, that's a natural thing. For each point, we want to know its closest neighbor. So this feels a little bit like proximity graphs, doesn't it? For each point, we are going to draw a directed line segment from it to its closest neighbor. Remember, yesterday we were talking about when points are mutual nearest neighbors. That would be certainly a natural thing one could approach with a KDS framework. You have moving points and now maintain the mutual nearest neighbor graph. But here we just have nearest neighbors. So you'll notice that some points are very popular. This point is the nearest neighbor of several points, but other points, P1 is not the nearest neighbor of anybody. P1 is out on the edge, but nevertheless, each point contributes, if there are no ties, one edge, so one directed edge. So it's very sparse graph. And we can't say anything about the n degree of the vertices. So the reverse k nearest neighbor problem, I think, is a very intriguing problem because it's simple, but it's not so intuitive. You have to kind of stop and think what it means a little bit. I think it's a very cool problem. You have a set of points in the plane or high dimensions, and now you have a query point. So the helicopter lands, person parachutes in to this set of points. So the query point, Q, is a new point that just dropped into the scene. And now what you want to know about that query point is for which of the points is the query point one of their nearest neighbors, or k nearest neighbors. So I'm standing here, and I want to know for which of you in the room am I one of your 3 closest neighbors? So I'm certainly not one of your closest neighbors. I'm not one of the camera person's closest neighbors. I might not be the closest neighbor of anybody, but I might be, well, you guys are sitting pretty close together. I might be your, oh, but she's behind you. I might be about your 5th closest neighbor. So if you want to know, and maybe I'm about your 5th closest neighbor. Actually, I might be about your 5th closest neighbor, Ali. 1, 2, 3, 4. Yeah, I'm about your 5th closest neighbor. So this query point, it might not be anybody's closest neighbor. If it lands way outside where everybody else is, it's not anybody's closest neighbor. It might be not even anybody's 3rd closest neighbor. But if I'm in the middle there someplace, I might be the 3rd closest neighbor of several people. That's the reverse K nearest neighbor. I think it's an interesting question. And you can imagine scenarios when that's of interest. So in Victoria, we're in an earthquake zone, and we're close to some volcanoes, and we have tsunamis from time to time. And people say we're due for the big one, the big earthquake. So there's actually quite a bit of talk, and I believe in Iran also you have interest in earthquakes. So there's a certain amount of talk about being prepared for disaster preparedness. And you can imagine scenarios in which you have some difficult situation and people are coming to help out, and people land in a situation and you want to know who is supposed to do what, which aid worker is supposed to help which people, and you want to know if a person lands in a certain place, for which other people around are they the best person to provide some help. It's a situation in which someone designing disaster relief might have questions like that. Also game-playing scenarios. In fact, we made a poster we contributed to a conference called Motion and Games. And it was people in computer graphics and games. And they liked this reverse K nearest neighbor question very much. And said, oh, that's interesting. Geometry people would come and talk to us. We like it that you came, and they had quite a bit of interest. I'm a character in a game. I'm playing a game, and I want to know for whom am I one of their closest neighbors. Game environments. Okay, so here is an example of the reverse K nearest neighbor question when K is equal to 1. So Q lands in the middle of the cows. No, lands in the middle of this population of points, and the question is, for which of those black points is the new point Q the closest neighbor? So Q is certainly not the closest neighbor at this point. In fact, what we're interested in is these 3 red points. So Q is the closest neighbor of this red point. If I draw a circle around this red point, it's empty, and Q is on its boundary. Similarly for this point and this point. Now notice there's nothing that says the radii of these circles have to be equal. No, not at all. This point could be quite a distance from Q, but it's over here. Q will still be its closest neighbor. So that's the reverse closest neighbor points. Okay, so what if the points are moving? How can we update that information about the K closest, for which points a query point is the closest amongst the K closest neighbors? So before Zahed came along, there was this kind of information about closest pairs. There had been some work by Gibas and Hirschberger and a student in the late 90s about maintaining closest pair information. And closest pair in all nearest neighbors was looked at by these famous people. This is the Euclidean minimum spanning tree, and this was part of Zahed's master's thesis with Ali Reza Zarai, kinetic Euclidean minimum spanning tree in the plane. And then for K nearest neighbors, all the K nearest neighbors, there actually was no previous work on kinetic data structures, and also for reverse K nearest neighbors. There'd been some work on k nearest neighbors, but not all the k nearest neighbors. And there wasn't any work on reverse k nearest neighbors at all. So some example results that came out of this work with Zahed was the first kinetic data structure for maintaining all the k nearest neighbors for any given k, not just k equals 1, any k. And then the first kinetic data structure to look at these reverse k nearest neighbors. And in fact, it does so for any k in general d dimension. So I think it's a nice problem. Okay, so one insight I think that's a useful technique in some of these problems, this general nice problem-solving strategy is we're trying to compute something. Sometimes a useful trick can be to compute more than you were trying to compute and then process the superset to find some superset of points, maintain that, and then have a fast way of winnowing it down to what it is you're really looking for. So what we're going to do in this case is to define a supergraph of the k nearest neighbor graph that's easy to maintain all the k nearest neighbors. Helps us answer the k nearest neighbor question. And we're going to use that to help us with the reverse k nearest neighbor question. So we're linking these two problems together. So at each point in this supergraph, we're going to maintain a list of the incidence edges ordered by the distance to p. So at each point in the supergraph, we're going to maintain a list of the edges where p is pointing to its the other points, and we're going to order that list by distance from p. So here's a supergraph for the k nearest neighbor graph problem. It's called the k semi-Yell graph. And the idea, I must warn you that pictures for this problem tend to be a little misleading, because what we're going to do is partition space at each point in the point set into some polyhedral cones. So in the plane, here's an example of one cone. And the cones are going to have small angle theta, where small means 60 degrees or less. So here's a cone, but now we're partitioning space. So this is going to be cone 0 here. We'll have a little notation later. And then there's going to be cone 1 and cone 2. We're going to break up space into six cones, index 0 through 5, around P. And I'm just drawing one of the cones. And what's kind of misleading about the picture is the cone, because it's easy to draw this way, is going to have its cone axis pointing along the x-axis. But keep in mind other cones will have different directions for their cone axes. And so what we're going to do inside each cone at each point P. And also each point P is going to have this partition of space into six cones. So lots and lots of cones, 6 times the number of points. So in each cone, what we're going to do is connect the cone vertex to the k points inside here that have the property that they have the shortest projections onto the cone axis. So you're not going to maintain their distances. We're going to just keep track of whose projection onto the cone axis is the shortest. And so that's going to be our k semi-Yell graph, that construction. At each point, go put 6 cones around it, and in each cone, put an edge in the graph from the cone vertex to each of the points that have short projections onto this cone axis. So this point over here is projection on the cone axis pretty far away, so it's not going to make it into the list of top 3 cone projections for this point P. So this is this k semi-Yell graph. It's a supergraph of the k nearest neighbor graph. You can prove this very interesting lemma, which is kind of a tongue twister, but is very useful. And it says, if you have a point P, and these pictures can be hard to understand too, because that somehow your brain, your eye, wants to focus on the cone vertex. And in fact, the star of the show is this point P. And point P, you see we're putting circles around P to indicate what's its closest neighbor. So this disk is empty. What's the second closest neighbor? What's the third closest neighbor? And so forth. So the star of the show, the focus of attention, is really on that point P. And what the lemma says is that if pk is the kth nearest neighbor of P, so here, let's say, in this picture you see P1, P2, P3. P3 is the third closest neighbor of P. It lies on the third ring out. And we're going to let W for wedge sub L of P be the wedge of that point that contains P. So in this case, P3 is the third closest neighbor of P. And so we're looking at the wedge of P3, and we're wanting to know which index to use. Well, very conveniently, what are we looking for? We're saying which wedge of this contains the point P. That's the star of the show. And in this case, it's wedge 1. I'm sorry, the wedge is the 0th wedge. Remember, we were going to index the wedges 0 through 5. So very conveniently, for drawing a picture, the wedge of P3 that contains P is the wedge 0. So that's this index L equals 0. And so we're looking at the wedge of P3. So this is wedge. This is an L, not a 1. So this is WL of P3, where L equals 0. That's what that notation means. So if P3 is the third nearest neighbor of P, then when you look in the wedge of P3 that contains P, so in this example, wedge 0 of P3, it turns out that P is among the 3 closest points to P3 measured in terms of projection on this axis. If P3 is the third closest neighbor to P, then when we look at the wedge of P3 that contains P, we'll find that the projection of P on the cone axis of P3 is in the top 3 in that wedge. That's the limit that gets used over and over again in Zahed's work. So, okay, how do we answer reverse k nearest neighbor queries? So we're given a query point, and we want to find the points such that Q is one of their nearest neighbors. So what we do is partition the space around Q into a set of cones. So here's, okay, in this picture the cones have changed a little bit. 1, 2, 3, 4, 5, 6, 7 cones. We have, oh, no, I'm sorry. This is cone 0, and that's the cone axis. Cone 1, 2, 3, 4, 5. We have those cones. And among the points in each cone around Q, we examine the k points that have short projections onto the cone axis. So this point has got the shortest projection onto the cone axis. Here, this point, here there's only 1 point. Here there's 2 points. Maybe this point has slightly shorter projection than this point, and so forth. So in each one of those cones, we around the new point Q that just dropped from the sky, we see what are the k points having the shortest projection onto the cone axis. And so what we're going to do is maintain the kth nearest neighbor of, which I'll call P hat, of each point in the plane. So before Q got there, I was maintaining the kth nearest neighbor of each point as a function of time. And now what we need to do is process the points in these cones and see if any of those points beat the kth nearest neighbor. We know the actual kth nearest neighbor for each of these points, or the distance from each point to its kth nearest neighbor. And now we just need to see if the new point beats that distance, in which case Q is among the kth nearest neighbors. So the idea is that this Super-Yau graph is maintaining an attractive list of candidates for us, because if Q is among the kth nearest neighbors at one of these points, then such a point will have a short projection on the cone axis in that cone. So it's a way of filtering what points to look at. All right, so that's all I'm going to say about that particular problem, that kind of classic geometry problem. Now I'm going to switch to a new problem. It's a problem about looking at graph drawing from a kinetic point of view. And this problem that we're going to look at is it's a kind of popular question at the moment in graph drawing for stationary points. And it's called point set embeddability. And I'm going to be showing you some slides. It was for a talk that Zahed was going to give at Microsoft Research in Washington State, but his visa didn't come in time. And so one of my other students had to give the talk, so we all worked kind of hard on this. And these are actually some combination of Zahed's slides and Nishat's revisions of them. So things are going to come flying out, and I'm going to jump back and say, oh, what was that? Because she likes to use animations. But anyway, here we go. I think these slides, I'm not going to go into a lot of technical detail, but I'll show you enough to give you an idea of what's a certificate. What do we mean by maintaining a certificate? How could that be useful? So let's take a look at this point set embedding problem without mapping. So here's the idea. You have a set of points, P1, P2, P3, P4 in the plane, and you have a graph, and this is an embedded, topologically embedded graph in the plane. So it's a planar graph. I don't imagine that V1, V2, V3, V4 are at fixed locations. It's just a drawing of this graph, a representational drawing, a cartoon drawing. But nevertheless, I'm interested in what the faces are. So I want V1, V3, V4 to be on a triangular face, and I want V2 to be outside that face. That's what I mean by an embedded graph. I don't mean that I have the coordinates of these points. I mean that I have the cyclic ordering of the edges at each vertex, and I know what the outside face is. That's what I mean by an embedded graph. So no coordinates here, just the information about the shape of the graph. What are the faces of that graph? So I'm given that information, and what I want to do is see, yes or no, can I somehow choose a point that's going to represent V3, and it doesn't have to be P3, it can be any of these points. That's what without mapping means. I just choose one of these points that's going to be the location where I'm going to place this vertex of the graph, and so forth. So for each point in the original combinatorial embedded graph, I want to find a place to put it on these fixed points that I'm obliged to use in such a way that when I draw the straight line edges that are given by this graph, I will get this topology, this face and this vertex outside the face. Is it clear what the problem is? Okay, so why are people in graph drawing interested in studying point set embeddability? Well, originally it came from saying, let's draw graphs on a grid. So there's this beautiful work a while ago by Pach, Defreshe, and Pollack that says if you have a planar graph, you can draw it on a grid. So each vertex maps to a grid point with straight lines, no crossings. In fact, you can use their algorithm and their technique for doing that as a way of proving Wagner's theorem that any planar graph can be drawn with straight line edges. So a while ago, people found a way to draw planar graphs on grids, and then they started competing. Who can get the lowest area grid? Can you get this width? Can you get this height? How big a grid do you need to draw your graph? So got to be a lot of interest in placing vertices of graphs on grid points. And then some other people started to say, well, why just look at grid points? Why not let the points be in any position you like and ask questions like that? What graphs can you draw on which collections of points? there's something called universal point set embedding. So you'd like a set of points such that you can draw any graph of a certain type on that set of points. Things like that arise. So grid points are universal for planar graphs. Here we have exactly in these embedding problems, you have the same number of points that you have in your graph. That's not true for grid drawing. You have lots of points, and you can choose which ones to use or not use. So this is slightly different. You're obliged to have exactly the right number of points to match with the number of vertices you want to draw. And yes or no, can you do it? All right, so here's an example. We might, and notice the indices are different. So this is to emphasize the point that this problem is without mapping. We're not saying V2 has got to go to P2. Then it would just be a question of testing, right? If we said V2 has to go to P2, V1 has to go to P1, we would just draw the picture and see if it was a good picture or not. It wouldn't be any question. So here we're allowed to put V2 anywhere we like. So one thing we could do is put V2 at P3 and V1 at P2, and we could assign the vertices to these points, and when we draw the structure, we would see indeed we have a triangle with one point lying outside that triangle and no edge crossings. We'd have a planar picture. So that would be an acceptable solution to the point set embedding problem without mapping for that little graph. Okay, now what happens if the points move? From time to time, this picture is going to be inappropriate as these points start to move around. So what can happen? There's their algebraic functions of constant maximum degree again. Related work. So here we go. There's the points are moving. Now I think it's kind of hard to see when the original mapping is becoming invalid, but I think you can imagine that it is from time to time. We need to do something. We need to remap the points, the vertices of the graph, to those moving points. So what we're going to do, that's kind of distracting. So just try that. So we're going to define a set of certificates. So one of our goals was to get a feeling for what's a certificate. So what's a certificate that says our current mapping of the vertices to the points is a correct one? We want to maintain some information about that. And then a critical event is going to happen whenever 3 points become collinear. So we're going to keep track of, going to make an event queue of 3 points becoming collinear because something bad might happen. So you can see here, for example, if I've forgotten which point V2. So V2 mapped to P3. So we're going to be in trouble if P3 swings around here and moves inside this triangle. Then we won't have an accurate picture. We'll have to redo things. Or if P3 moved all the way out here and then came over here, we would have some line crossing. P3 would be outside the triangle, but we'd have a line crossing. We have to do something. There's a nice animation here. So let's see that. So here's a certificate. What we're going to do is look at the outside vertex P2, V2, at P3, and it's attached to some point vertex P2 that's hosting V1. So we look at the point that's hosting vertex V1. And now we're going to look at the cone of that point that's hosting V1. And we're going to call that the wedge of P2. And what we're very interested in is when P3 is outside that wedge. There's a nice, simple example of a certificate that's going to prove for us that our current mapping is correct. If P3 lies outside this wedge, then we have our desired structure here of a triangle with the missing point outside. I also need to require P3 is outside this wedge, because if it were in here, then I'd have an edge crossing, which is not what I want. So my mapping, my assignment of who's hosting, which points are hosting which of these vertices, is correct if and only if the host for vertex V2 lies outside the host for the wedge of the host for V1. So very, very simple, nice example of a certificate. And look at this nice animation designed by Nishat. Here, a bad situation, P3 just moved inside the wedge, and so what we need to do is reassign the mapping of which points are hosting which vertices. So we can do something like that. Now we have a new way of drawing this graph on these points, and the host for vertex V2 is now outside the wedge for, now I need the wedge for P1 here I need to maintain. And there's the wedge for P1. V2 is adjacent to V1. The host for V1 is this. I look at the wedge of it defined by it connected to the other 2 points, and I have the certificate that the host for V2 is outside the wedge for the host of P1. So that's my new certificate. I want to maintain that certificate. That's the idea. So here's an example. The other bad case, we need sound effects here. P3 lies in the wedge of P2, but outside the triangle. It's still bad because we have a crossing there. And so what happens in this scenario, we have to remap who's hosting which vertices, and we can do it like this. And now if we assign the vertices like that, so it's P3 that's hosting V2, and P1 that's hosting V1, then we have P3 outside the wedge of P1. So that's a new valid certificate. We want to make that Boolean value evaluate to true. And then when it's no longer true, then why not? Because P3 has moved inside the wedge, so that means P3 has got to become collinear with P1, P4, or P3 has got to become collinear with P1, P2. When one of those collinearity happens, disaster, we have to change things. We have an internal event. All right, so KDS measures of performance. We already talked about those. So let me just briefly describe, without going into technical detail, how people in graph drawing go about mapping vertices, graphs onto points. So what they do is take the points that you got to map your graph onto and sort them by x-coordinates, say. Then you take your graph, so this is a combinatorial embedded graph, and find a Hamilton cycle. If it doesn't have a Hamilton cycle, you make a Hamilton cycle by adding some dummy vertices. And then you take that Hamilton cycle and assign the vertices on the Hamilton cycle to your points according to their x-coordinates. And of course, P12 has to come back and finish the cycle back at P1. If I number the vertices in the same order as their x-coordinates of the points. And then here's a dummy vertex. And the dummy vertex, I'm going to add a new point to my point set that's at the midpoint of the 2 original graph points that I put that dummy vertex in the graph between. So I get a picture like this. There's my graph, and there's my point set down below, and I take that Hamilton cycle and I map it onto these point sets. And then the idea is the Hamilton cycle with the dummy points creates an inside and an outside of the cycle. And the points on the inside of the cycle I'm going to put above this path, ordered by x-coordinates, and the other points I'm going to put below. And if I'm clever about it, by choosing the slopes, I can get a drawing that doesn't have any crossings and only has a couple of three bends. I might have a bend up here, and then if I have to go through a dummy vertex, I pick up another another bend there. So that's the rough idea of how people were solving this problem before. Mind you, this is a typical example of a really ugly drawing you can get from some clever graph drawing technique. So, okay, so we maintain dynamic kinetic tournament trees about the slopes of the edges involved. And here's an event where something happens. So what's going to happen, the critical event, where we have to make a change, is if 2 points that are moving, these are the moving points, if they change their x coordinates, then we have to do something. So we get a situation like that, now we have crossings. So basically what has to happen is that the edges that used to be adjacent to QI have now got to become adjacent to QJ and vice versa. They just have to trade off which edges they're hosting the endpoints for. So that's an ordering event. And then, okay, so I'm not going to go through these technical details. Let me just get to the end. Performance analysis, so we got a good performance analysis. We got an efficient, responsive, compact, local kinetic data structure for solving this problem. We can also do it for 2 bend drawings, but the kinetic data structure we got does not satisfy all the 4 performance criteria. So one problem would be do this for 2 bend drawings, but find a way to satisfy the performance criteria. Find kinetic data structures for straight line drawings of some special kinds of graphs, like outer planar graphs and trees. And then also down here, of course, propose meaningful kinetic data structure problems for problems and graph drawing. We were hoping just to have an example. A problem like this would generate people's interest in the graph drawing community and kinetic data structures. So I think it's wide open to suggest graphs that you would like to draw on moving point sets. For example, if you have those birds flying around, you might like to map their family trees onto those moving points and maintain that. So you could look at it if you're a biologist studying the relationship between family relations amongst the birds and how they fly. Is there one? You might want to map vertices in your graph to specific points and then maintain the structure of that without much edge crossing. Okay, so thank you very much for your attention, and also I'd like to thank you for your wonderful hospitality and your friendship here. I've met so many nice people, and thank you very much for the chance to participate in your school. Question? Oh, it has, in general, it might have high degree. So all the incoming edges for the one vertex has got to be changed over. The 2 vertices have got to change which edges they are endpoints for. They've got to change which vertices of the graph they are hosting. So each point is hosting a vertex of the graph. And now these 2 points change places, so they have got to host different vertices from the graph. They've got to just change which 2 vertices they're hosting. So this point and this point, they're moving around. This one says, I'm hosting vertex 3 of the graph, and this one says, I'm hosting vertex 5. Now they change their positions. So now this one says, I'm hosting vertex 3, and this one says, I'm hosting vertex 5. And because the points have changed which vertices they're hosting, that implies that edges for those points will be different. So this point's hosting vertex 5 now. So all the edges that are endpoints that are incident to vertex 5, now they come into this point instead of this point. It's just like these 2 vertices are holding endpoints of edges, and now they have to just swap which edges they're holding. that it's kind of it's a little bit too technical to follow very rapidly on the fly, but I can come up and explain with the picture if you like. We can see what's going on there. Yeah. The basic, maybe the idea that or key thing that you're missing is that we order the vertices along their Hamilton path that we created in the graph, and we're using the same indices for the points. So if 2 points change positions, well, the order in the Hamilton cycle didn't change, so I have to change which point in the plane is hosting which vertex. If vertex 3 came before vertex 4, then vertex 3 has got, in the Hamilton cycle, then vertex 3 has got to go to a point that comes x-coordinate less than vertex 4. But if those 2 points change locations, then vertex 3 has got to go to the point that's third in x-coordinate order. That's the idea. It's not to do with the degree of the vertices. Please.
What is the relation between reverse nearest neighbor graph and kinetic graph?
Okay, so the idea is it's an interesting question for stationary points, even points that aren't moving. I have a new point arrives, and I want to know for which points, existing points, is it one of the 3 nearest neighbors of those other points. So now I just ask the same question when the points are moving. So here I have the cows are moving in the field, and the farmer helicopters in. And now we want to be able to say for which cow is the farmer one of the closest neighbors. So they're moving around. So we're trying to do disaster relief, and the people are moving around. They're moving around as best they can, and now some aid worker arrives. We want to know which of those points is it one of the closest neighbors. Then it can help. People try to help each other, but the aid worker, for which points is the aid worker the nearest help available? But points are moving. So it's a shift from looking at the stationary problem to looking at the same problem in a kinetic framework where the points are moving. That's all. It's the same with any of these problems in kinetic data structures. You have some basic stationary point question, and now you ask the same question, but you let the points move. See what you can say. Oh, well, you certainly can ask the question. Yeah. You certainly can ask the question. Yeah. I'm not claiming the results would work, the same techniques would work, but you can certainly ask the question and study it. Yeah. You could ask a Euclidean metric, the Manhattan metric, for example. Yeah.
Your first slide, you said something about
Yes, you could do that. So maybe your points are going to move along polylines, and so you'll know x of t and y of t are linear functions for a certain period of time, and at the end of that time interval, now they move down another edge of the polyline, so they become different linear functions at that point in time. Yeah, you can do that. So for certain intervals of time, every point would be moving along straight line trajectory, but at certain points in time, they would start to move along other straight line trajectories, and you could say when those moments in time would occur. So you could say the points are moving along polynomial functions of bounded degree in intervals of time, but you don't want too many intervals of time. You could discretize the intervals of time and say within any specific interval of time, that's the model. And then you move to another interval of time and you get another collection of polynomials.
That affects the time and space of
Yes. Yes. Not in this model. Not in this model. If you want to move along polygonal lines, maybe you would be happy with a polynomial approximation to your polygonal curve. You put in some little roundy bends. But if these are highways, you can't cut the corner too. Always the question, what model to use that's simple enough to do the job that you want to do, and strong enough mathematically to facilitate the analysis you want to do. Thank you for your questions. And I think now we have a break. I'm happy to answer any other questions. You just in the break. Thank you.